Hey there, and welcome to this mini course on working with data frames, the core data structure in Python's powerful Pandas library. Now, since you just clicked on a video about pandas, I'm assuming you're aware that it's a Python library specifically designed for data transformation and analysis. And from my personal experience, it is in fact one of the most powerful tools for data analysis you'll find anywhere. So it probably goes without saying, but I'll say it anyway, that Pandas needs us to feed it data to be useful. On its own, without any data to chew on, so to speak, it just doesn't do us much good. But it's actually a very specific kind of data that Pandas thrives on: tabular data. The kind that's organized neatly into a grid-like structure of labeled columns and rows, kind of like you'd expect to see in a spreadsheet or database table. And that leads us to perhaps the foundational data structure in Pandas: DataFrames. Just about everything we do in the course from here on out is going to involve DataFrames in some form or fashion. So it's important to lay just a little groundwork before we jump into some actual coding examples. So first things first, what the heck are DataFrames? So a Pandas data frame is essentially a supercharged table. It's a flexible, two-dimensional data structure that allows you to store and manage data in a clean and organized manner, in good old-fashioned rows and columns, just like a spreadsheet or a database table. Plus, you can label these rows and columns with meaningful names to make your life even easier. Data frames also come with a boatload of built-in methods for data analysis and manipulation, making it a breeze to slice and dice your data just the way you want. Need to filter out some rows? Calculate the median of a column? Or maybe merge and join multiple tables? Pandas makes these kinds of data-intensive operations easy, at least compared to the kind of programs you'd have to write to accomplish the same things without Pandas. And just as importantly, Pandas is optimized for working with data, so it's able to manipulate large data sets much faster than with traditional Python. The bottom line is, if you've got a treasure trove of data, specifically data that can be organized into rows and columns like a spreadsheet, and you need to analyze, manipulate, or visualize that data, Pandas data frames are the way to get the job done in Python. So let's dive right in and see how all this works. So here, I've created a new Colab notebook for this video, and if you want to follow along, just create your own Colab notebook in your own Google Drive. And to save us a little time, I've also already connected this notebook to a runtime, so we should be able to start running our code right away. Now, speaking of that code, before we can start playing around with Pandas data frames, we'll first need to import, well, Pandas. Now, by convention, we usually import Pandas with the alias PD. So I'll just type in this very first cell, import Pandas as PD. And then run that. So with Pandas imported, we can turn our attention to creating our very first data frame. Now, there are a number of ways to create a Pandas data frame, perhaps the most common of which is from some kind of external data source, like a text file, spreadsheet, or database table. However, just to get started, we'll actually create one from scratch. So this can be done by converting a specially structured Python dictionary into a data frame. Now, to save you from watching me hunt and peck around my keyboard for 20 minutes typing this out, I'll go ahead and paste in an example dictionary to show you what I mean. And I'll do that in a new cell. So I'll just add a new code cell and then paste in that dictionary. Now, as you can probably see, this dictionary contains information about 4 household pets, their favorite snacks, and the cost of those snacks per month. As an aside, I can neither confirm nor deny that this data is accurate, but what I can confirm is that owning pets is a lot more expensive than you think. They are cute little guys, though. So zooming in on the structure of this dictionary, you'll see that the general categories, those being pet name, species, favorite snack, and monthly snack cost, are the dictionary keys, or labels, whereas the actual data points associated with these labels are contained within lists assigned to each label. Now, when we convert a dictionary structured like this to a data frame, each key value pair in the dictionary is effectively converted to a column in the table, where the dictionary keys are the column headers, and the data points in the associated lists are the values in those columns. Now, this means it's important for each list in the dictionary to have the same number of values, so each column in the resulting data frame has the same number of rows of data. But enough theorizing. Let's see how this actually works in code. So now, to create a Pandas data frame from this dictionary, we'll first assign it to a variable. Now, although this step isn't strictly necessary, it makes the resulting code much cleaner. So before our dictionary definition, we'll just say data equals, which will effectively assign this dictionary to a variable called data. And then I'll run this cell, and then create another new code cell. And here, we can now use Pandas' built-in DataFrame function to convert this dictionary into a data frame. The DataFrame function will simply take our dictionary as its argument and spit out a shiny new data frame. So this DataFrame function is actually a method that belongs to the Pandas library, so we'll call it from the Pandas library, which we can do with dot notation by saying pd dot DataFrame, and then we'll simply pass in our dictionary stored in that data variable as the one argument. Then finally, I'll assign the result of calling this DataFrame function with our dictionary as its argument to a new variable that I'll call df. So now let's run this code cell. And now, to see what's stored in that df variable, I'll create one more code cell and simply reference that variable in that cell. And then if I run the cell, Pandas will show me the result of whatever expression is on the last line of code in this cell. And in this case, we've only got one line of code, which contains the simplest kind of expression possible, which is just a value stored in a variable. So if we run this, as you can see, we get back a beautifully formatted table, organized into neat rows and columns formed from the data in our dictionary. And, as you'll see in great depth in the sections to come, this data structure you see here lends itself to all sorts of cool methods for slicing, dicing, and analyzing the data contained within it. Now, one thing I want you to take note of here is the very first column of the data frame, which appears to have simply been conjured out of thin air. After all, I do not recall defining a column with the values 0, 1, 2, and 3 in it. Well, this mysterious column is actually called an index, and it turns out that these indexes are an essential part of every data frame. Now, by default, Pandas assigns data frames what's called an integer index, also known as a range index, which is just a sequence of evenly spaced integers. These range indexes start at 0 and increment by 1 for each subsequent row, which obviously is the exact pattern you see here. So indexes are an essential aspect of working with Pandas since they serve as a unique identifier for each row and enable efficient data selection and manipulation. Now, while this kind of sequential numeric index is the default in Pandas, it's important to note that Pandas indexes are versatile and can take various forms, like strings, dates, and even multi-level hierarchical indexes. Now, all of these can make our data easier to analyze in different ways and from different angles, as we'll explore a bit later on. But for now, I think we've got the basic concept of data frames down. So we're ready to learn about a more realistic and common way of creating data frames from data we fetch into Pandas from an external file. That's coming up. I'll see you then. So as we've established, Pandas is all about working with table or spreadsheet-like datasets. So in order to really learn Pandas, we're going to need just such a dataset to work with. Now, just to make sure we get experience working with different types of data, I've actually chosen 2 datasets for us to work with. And I think they are in fact about as different as 2 datasets could possibly be. Now, what you see here is our first example dataset, which contains a ton of information about home sales in King County, Washington, in the United States, which also includes my personal favorite city of Seattle. Now, this dataset, which is in fact a real-world dataset containing information about real-world home sales, includes information like the sale price of the houses, the date of the sale, the number of bedrooms and bathrooms, the square footage of the living space in the lot, the number of floors, and so on and so on. It's pretty much an analyst's dream, a veritable treasure trove of information to work with. Now, flipping over to our second example dataset, this one, which is also a real-world dataset, even if you might be a bit skeptical about whether the subject of the dataset is real, contains information about UFO sightings across the globe. This information includes things like the date and time of the sighting, the geographical location of the sighting, whether that be city, state, or country, the shape of the UFO, the duration of the sighting, and in many cases, comments that contain a description of the event. Now, the structure of this dataset is such that each individual row, or record in database speak, pertains to a single unique sighting. Just like, going back to our King County house sales dataset, each record here pertains to a single house sale in King County, Washington. Now, you'll be getting to know both of these datasets throughout the course. But of course, in order to work with these datasets in Pandas, we've first got to get them into Pandas. We'll tackle that in the next video. See you then. So most of the time when we're working with Pandas, we'll be creating data frames from external data sources, instead of from scratch like we saw in the first video of this section. Those external data sources often include things like text files, like the one you see here, or even spreadsheets or relational databases. Now, just looking at the sheer volume of data in this one little text file, both in terms of the number of columns and the number of rows, you can see why we wouldn't want to create a data frame based on this much data manually. Even if you're a good typist, just imagine what it would be like to put together that Python dictionary. So while spreadsheets and databases are sometimes used as data sources for Pandas, arguably the single most common method of storing and sharing tabular data is good old-fashioned text files. And that's largely because text files really just do one thing, and that's store data. Spreadsheets have lots of additional functionality, including formulas and charts and pivot tables, while databases have their own kind of specialized functionality. But a text file just stores data. Now, since, if you aspire to be a Pandas data analysis guru, your future is going to include lots of text files, it's worth digging into the structural features that text files tend to have in common. First is that text files commonly have headers. These headers essentially define the columns of the dataset. Now, the other common feature is that the individual data points in each row of the data set are separated by some kind of delimiter. Now, in what is probably the most common flavor of text file, commas are used as the delimiters to separate the values in each row of data in the file. And that's exactly the kind of file you see here. In this data set, commas are used to separate the individual headers in the first row of our data, which contains those column headers. And then commas are also used to separate the data points in each row of data underneath those headers. Other fairly common delimiters you'll find in the wild are the pipe symbol, which is basically a vertical bar that can be fairly tricky to find on your keyboard, or a simple tab character. But again, commas are the most common delimiter that you'll find. Now, comma delimited text files like the one you see here are so common that they actually have their own file extension, CSV, which stands for comma separated values. And because that file type is one that anybody who works with Pandas regularly is apt to encounter frequently, Pandas has a built-in method for fetching these types of CSV files directly into DataFrames. And that is called, quite intuitively, the read CSV method. So this read CSV method gives us a simple, convenient way to extract data from a CSV file into a Pandas DataFrame with just a single line of code. The method takes just one mandatory argument, which is the path or location of whatever CSV file we're trying to import on our computer. Or, in the case of Colab, that file's location within our Google Drive. Now, speaking of which, I've already saved this CSV file here, which, if you didn't recognize it before, is just our King County house sales dataset in its rawest form, to a folder on my Google Drive, which will allow me to access it from a Colab notebook. Like this one, for example. Now, if you're following along, you'll want to save that King County house sales CSV dataset, which you should be able to find in the course resources, to your own Google Drive. Now, before we can access a file from our Google Drive here in Colab, we first need to mount Google Drive within our Colab notebook, which, conveniently enough, can be accomplished with literally a few mouse clicks. So first we click this folder icon here that represents files, and then we hit this little icon here that looks like the icon for Google Drive. And what this is doing is telling our Google Drive to give access to itself to this Colab notebook. So we'll just click this, and then we'll hit Connect to Google Drive to confirm that we do in fact want to permit this notebook to access our Google Drive files. And after that process is complete, which normally takes a few seconds, we'll be able to access any files from within our Google Drive right here in this particular Colab notebook. Now, to be sure, there is another, slightly more direct option for accessing external files in Colab, which you've already seen if you watched the brief introduction to Pandas in the last section. But that method involves session-based storage, in which you import the file directly to your notebook, but then that file will promptly disappear and later need to be re-imported after you close the notebook. Whereas mounting your Google Drive from within this Colab notebook allows the notebook to access data files stored anywhere in Google Drive even after you've closed the notebook and reopened it. So for any work you're doing where there's any chance you might want to look at it again, taking the extra step to mount your Google Drive within the Colab notebook you're working in is obviously more than worthwhile. Okay, so now that we have access to all the files stored on our Google Drive, and as I've established, I've already uploaded that King County house sales CSV file to my Google Drive, the next step is to identify the exact path that defines where that file is located on my Google Drive, we'll need to be able to supply the readCSV method that information in order for it to read the file. But since I've already mounted Google Drive in this Colab notebook, I can actually navigate through my Google Drive here to find where the file is located, right here in my Colab notebook. And here, several folders deep inside my Google Drive, is where that King County House Data CSV file is stored. And to get the exact path, I can just click these three little dots to the right of the file name and choose Copy Path. And now I can close out of this Files sidebar altogether. And what I'll do next is just capture that file path in a variable that I'll call path. Now, of course, I could have just fed this path directly to the readCSV method, but I generally find it cleaner to put something this long and messy into its own variable. So now I'll run this cell, and then in another cell, I'll import pandas, and as usual, alias it as PD, and run that. And then finally, I'll call that readCSV method on the pandas library, and then pass in our path as the argument. So now the moment of truth. Let's run this cell and see what happens. And as you can see, the readCSV method has successfully parsed that messy-looking text file into a clean, easy-to-read table divided into rows and columns. Now, the readCSV method is really smart. It was able to correctly parse the column headers in our text file, as well as the data points belonging to those columns. And just to underline the transformation, I'll quickly flip back to our original text file, and you can see how all of these values that are separated by commas in each row of the text file, including the row containing the column headers, have now been parsed into an orderly matrix of rows and columns. Now, a couple things to note here. Pandas, by default, guesses that the first row of data in the source CSV file contains column headers, and it gives those headers special status, as you can see here, just by how they're displayed in the DataFrame. Now, sometimes we're not lucky enough for our text files to come with column headers built in, but that's a topic for another video. The next one, in fact. But back to the task at hand, the other thing I want to point out here is that what we see when we run this line of code is not the entire data set, but rather a preview of the data set. Now, the CSV file we just read into a DataFrame has 21,613 rows, and Pandas doesn't want to break our browser by showing us all that data at once. So instead, it just shows us the first 5 records and the last 5 records. But don't worry, there are all sorts of sophisticated methods built into Pandas for parsing out slices of the data frame we might be interested in, or summarizing and aggregating the data frame to make the sheer size of and scope of the data more manageable. Now, another thing to consider about readCSV, given that we've already established that text files can use other characters as delimiters besides commas, you might be wondering how we would be able to import those datasets into Pandas. Well, we can still do that with the readCSV method. We would just need to include an additional optional argument. So for example, if the characters separating the data points in our text file were pipe symbols, for example, instead of commas, we would need to tell the readCSV method to look for that separator instead of a comma, which we would do by adding another argument, and this will be a named argument, which means we're basically telling Pandas which additional piece of data we're supplying to this method. That's necessary because readCSV, like many methods in Pandas, has a ton of optional arguments that we can provide it. So in order to tell the readCSV method which of those optional arguments we're supplying, we need to specify the name of the argument. Now since, as I mentioned, it is quite common for Pandas methods to have multiple optional arguments, these named arguments, also sometimes referred to as keyword arguments, are something you'll be seeing a lot of in future examples. Consider yourself warned. So in this case we have right in front of us, the name of the argument is sep, which stands for, as you might have guessed, separator. So we would just say sep equals, and then whatever that non-comma separator is inside of quotes. Now in our case, our data is separated by the more conventional commas, so we don't need this additional argument. But it's worth knowing that you have this option in case the data in your text files are separated by some other kind of delimiter. So one last thing I want to point out before we go. The reason we got this preview of our data frame when we ran this line of code is that the read CSV method returns the data frame that results from calling it. So when that's the last line of code in the cell, as it is here, we get a preview of that data frame. However, if we assign the return value of that read CSV method to a variable and then rerun the code, nothing is displayed. So if we assign the return value of that read CSV method to a variable, in order to get the preview we just saw, we need to reference that variable in the last line of the cell before we run it. Now, since that variable, which contains a data frame, is the last line of code in this cell, when we run it again, now we get the preview of our data frame once more. Now, since storing our data frame in a variable like this forces us to take that extra step to get the preview of the data frame, you might wonder why we would want to store a data frame in a variable at all. Well, as you'll see very soon, there's actually a huge advantage to storing data frames in variables. It makes referencing them, and most importantly, manipulating, transforming, and extracting data from them much easier down the road. And for that reason, we'll pretty much always be assigning our data frames to variables from here on out. So as I touched on in the last video, it's sadly the case that not all text files come with handy column headers that tell us what's in each column. And in those cases, it's up to us to provide our own column headers, since a bunch of columns of data aren't worth much if we can't tell what's in each column. Now, fortunately, we can specify our own column names in the form of a list as part of the data import process via the read CSV method. But before we see how that works, let's see what it looks like to import a text file with no column headers into a Pandas data frame with the read CSV method. So here I have a Colab notebook that I've already mounted my Google Drive to. And here in the first code cell, I have the path of a version of that King County house data CSV file that just happens to not have any column headers. And I've saved that path to a variable, as you can see, called noHeadersPath. So I'll run that cell, and then I'll import pandas in the very next cell. And then in another code cell, I'll try using the read CSV method to import that file into a data frame and preview it. So I'll say noHeaders equals pd.readcsv, and then I'll pass in our noHeadersPath. And then to preview the data frame, I'll just reference that variable that we're storing the return value of the read CSV method into. And now running this, you can see how the read CSV method assumes that the first row of values in our CSV file contained headers. But since it didn't in this case, we end up with what is effectively just a random row of data that is both formatted as headers and will be treated as column headers behind the scenes by Pandas. That means, for example, that this very large number you see as the column header, so to speak, for the very first column, would not be included in any calculations we might want to do against that first column. As far as Pandas is concerned, 712930055520 is a column header, just the same as the words that were used as actual column headers in the examples we saw in the last video. So this is obviously not a sustainable state of affairs. We need meaningful column headers to make sense of our data. So if we don't have those in our source data, we have to provide them ourselves. And fortunately, readCSV has yet another optional argument that makes it easy for us to do so. Now, the first step is to define a Python list that contains headers for all the different columns in our text file. Now, to show you what that looks like, without you needing to watch me struggle to type for the next 30 minutes, I'll just go ahead and paste in a pre-written list into a new code cell. And I'll do that prior to our cell where we use the readCSV method, since the readCSV method will need to be able to reference this list. So as you can see, we have one value in the list per each column in our data, and the order in which those values appear should align with the order of the columns in our data. Pretty intuitive stuff. Now here, I've just gone with the exact original names from the King County house sales dataset, but if we didn't like those names, for example, if I wanted to change ID to sale ID, this is the perfect opportunity to do that. So now that we've defined our list here, I'll run that cell, and then down in our call to the readCSV method, I'll add that optional argument, which is called names, and to that, I'll simply pass in our headers list. So now running this cell one more time, sure enough, now we have column headers again, and we've customized the name of that very first column header because that optional names argument gives us the ability to make those column headers really whatever we want to call them. Now it's worth noting that even if your source text file already has column headers, it's still possible to override those existing column headers using this optional names argument of readCSV, just like we did here. But doing this is generally more convenient after we've already fetched the data into a data frame. We'll see an example of this a bit later on. So sometimes, really the vast majority of the time, the simple preview of a data frame that we get in our Colab or Jupyter notebooks by default just doesn't give us the information we really need from a data set. I mean, if it did, we probably wouldn't need a whole course on pandas. So while there are all sorts of intricate and complex methods for squeezing exactly what we're looking for out of a data frame, and we'll be going over the most useful ones throughout the rest of the course, sometimes we don't even know exactly what we're looking for. Now, Pandas has all sorts of intricate and complex methods for squeezing exactly what we're looking for out of a data frame, and we'll be going over the most useful ones throughout the rest of the course, but sometimes we don't even know exactly what it is we're looking for. In those cases, what's often needed is simpler methods that just give us some basic general information about that data frame to help us orient ourselves and provide a baseline and jumping off point for more in-depth analysis. And those are just the sorts of methods that we'll tackle over the next couple of videos. Now here you can see that I've taken the liberty of creating a new Colab notebook for this video, mounting Google Drive in it, and fetching our King County home sales dataset into a data frame. Now if you want to follow along with the video, feel free to just pause it right here and follow these same steps to import that dataset into a Pandas data frame. But back to the task at hand. Using built-in DataFrame methods and properties to inspect Pandas DataFrames from different angles. Now, one DataFrame property that can prove more useful and informative than you might expect is the columns property, which simply lists out all the columns in the DataFrame. Now you might think, well gosh, we can see all these columns right here in the preview, but actually if you look carefully, you'll see there's an ellipsis between the view column and the grade column. And that's because for larger data frames with more columns, like this one, the preview you see in the Jupyter Notebook may not show you all the columns. So to get a list of all those columns in the data frame, all we'll need to do in a new code cell is simply say house sales dot columns. Now we won't need a pair of parentheses here after columns because this is not a method. It's simply a property of the data frame. So now if we run this cell, now we get a complete list of all the columns in the data frame. Now there can be other advantages to having all of our data frame columns fetched into a nice, neat list-like data structure, but that's not something we'll worry about for now. Now another useful piece of information we can get about a data frame is its length, which is another way of saying the number of rows in the data frame. So to get to that, in a new code cell, I'll simply type the name of the len function and then just pass in our house sales variable that contains our data frame. And now running that, we get the number of rows in the data frame. Now to get a little bit more granular than that, we can call the shape property on a data frame, which will return a tuple whose first value is the number of rows in the data frame, and the second value is the number of columns. So now, with one line of code, we've got a pretty good read on the dimensions and overall size of the data set we're working with. Now, if what you're looking for is more of a general preview of the data frame, we can use either the head method or the tail method. We'll start with the head method, and you can see that it's a method because we have to put a pair of parentheses after it. So now running that, we get, by default, a preview of the first 5 rows of the data frame. Now you may have noticed that this is pretty much identical to the preview that we get of a data frame by default. The only difference being we actually don't get the last 5 rows of the data frame. So what, you might ask, is the advantage of this method over the preview we get of a data frame by default? Well, for one, we can actually specify the number of rows that we want to see in the preview by passing in an optional argument to this head method. So if I pass in the number 10 and then rerun this cell, now we get a preview consisting of the first 10 rows of the data set. And as I alluded to a moment ago, there is a corresponding method called tail, which, as you might have guessed, works just like head, except it pulls the last n rows of the data frame. So if I run that with 10 passed in as the optional argument, we now see a preview of the last 10 rows of the data frame. Now another way these head and tail methods can come in handy is if we actually want to treat this preview of the first n rows or the last n rows of the data frame as its own data frame. Just as an example, let's say you're dealing with a truly massive data set and you just want to sample the first, say, 100 rows of that data set to do some preliminary analysis on, or perhaps export to a spreadsheet program like Excel. Well, it turns out that the head and tail methods actually return a brand new data frame that consists of either 5 records if we don't pass in an argument, or if we do pass in an argument, the exact number of records we specify. So let's see what happens if, in a new code cell, I actually assign the result of calling the head method on our data frame to a variable. So I'll say preview equals, then I'll call the head method on our house sales data frame. And just for example's sake, I'll preview the first 7 rows of that data frame. So now running this, nothing happens at first, but now let's see what the type of the value stored in that preview variable is. And sure enough, it's a data frame, meaning that we can work with that preview consisting of just the first 7 rows of our data set in the same way that we can work with the overall data frame or any other data frame for that matter. Okay, so that's it for our first go at inspecting data frames with built-in properties and methods. Up next, we'll dive a little deeper using a method that gives us even more information about the data frame we're working with. So in this one, we're going to look at another method that can be used to inspect data frames, one that returns a lot more information than the methods we've worked with so far. Now that of course begs the question of why I didn't just start off with this method and skip right past the ones we looked at in the last video. Well, that's because working with the info method requires that you have some understanding of a fundamental concept of data frames that we haven't covered so far, and that is data types. So in contrast to other applications you may have used to work with data, like spreadsheets for example, in Pandas DataFrames, columns are assigned exactly one data type. You know how in an Excel spreadsheet, while it's not exactly a best practice, people commonly put all kinds of different data in a single column? Well, Pandas DataFrames are designed to prevent that exact type of disorganized data structure. And to that, once a data type has been assigned to a column, all values in that column must be compatible with that column's data type. If you've done any work with databases, this may remind you a bit of how much more restrictive databases are than Excel spreadsheets, for example, when it comes to what kind of data you can store in what column. Okay, so now we know that Pandas DataFrame columns each are assigned a data type. But given that, it might also be useful to know what kinds of data types exist in the Pandas universe that the columns in our datasets might be assigned to. Now, there are actually quite a few different data types in Pandas, but there are 4 that you'll see most often that are the most important to understand. The first is int64, which is assigned to columns containing integer values, like 1, 22, 51, and so on. Next up is float64, which is used for floating point or decimal values, like 0.01, 3.14, 11.11, and so on. Then there's the date times 64 data type, which, naturally, is used for date and time values. And then finally, we have the object data type, which is used for both text strings, things like the names of people and places, and for columns that just have mixed data types where not all the values fit into one of those previous 3 categories. So say, for example, you imported one of those Excel spreadsheets where somebody had put all different types of data in a particular column. Well, Pandas would assign that column with an object data type, because not all the values are integers, not all the values are floating point numbers, and not all the values are dates or times. Now, whether we create a data frame from scratch or create one based on an external data set like we've been doing with the read CSV method, Pandas will assign these data types to the columns in that data frame automatically based on the data it sees in the columns. But as you'll see soon enough, we also have the ability to override Pandas' choices and assign data types of our choosing, with the only restriction being all the values in that column have to be compatible with that data type. Now, the type of data type that we choose for a column, assuming that there are multiple data types compatible with the values in that column, matters for, among other reasons, the size of the data being stored. For example, integer values like 1, 22, and 51 are perfectly compatible with the float64 data type in addition to the int64 data type. However, the same values stored in an int64 field will take up less space, since Pandas won't have to worry, so to speak, about precision after the decimal place. Now, even more importantly, there are certain kinds of analytical operations, think sums, counts, averages, and more, just for starters, that only make sense on numeric data types. So if you find a field in your data frame that's assigned an object data type, but contains mostly numeric values, it may be worth your while to look into converting that data type to an int64 or a float64. Much more on this shortly, by the way. But for the moment, since we now understand this concept of data types in Pandas, as well as the 4 most common data types you'll see, it's time to introduce the DataFrame method that this video is really all about. The info method, which provides, well, info about the data types of our DataFrame columns, along with a bunch of other stuff. Let's see how it works. So here in a Colab notebook, I've done all the usual setup, importing Pandas, extracting the path of our King County house sales dataset into a variable, fetching that dataset into a data frame, and then previewing it. So with that data frame captured in a variable, I'm going to jump right into calling the info method on that variable. So I'll add a new code cell, and I'll simply say house sales.info. And I will need that pair of parentheses after the name of the method, since it is a method and not a property. So now running this cell, and then scrolling up a bit to see the output, we see that, like the columns property, the info method gives us a list of all the columns in the data frame, but it also tells us, all the way over to the right, the data type of each column. And as you can see, Pandas assigned an int64 to the ID column, which makes sense, a float64 data type to the price column, which also makes sense since prices can have a decimal component. And going on down the line, it looks like all of the remaining columns were assigned either an int64 or a float64, except one, that being our date column, which was assigned an object data type. Now again, the object data type is typically used to store either text strings or a mix of strings and non-strings in a data frame column. But that's not the case with our date column, at least it's not supposed to be, since it's actually supposed to store, well, dates. But what you'll find is that it's very commonly the case that Pandas guesses int and float data types correctly, but often converts date and date time values to an object data type, even if they're valid dates and times. So in short, while the object data type is correctly applied to string data, like, again, the names of people, places, or things, it is often inappropriately assigned to data that Pandas, for whatever reason, did not correctly interpret as date-time data. You can think of it this way. Pandas likes working with values that you can do calculations on, like numbers and dates. And it wants, to the extent that it has feelings, to convert the data in the columns of our datasets to one of those three data types: int, float, or date/time. But if it's not able to parse the data in a column as one of those big three data types, it will use the object data type as a kind of fallback. But it's worth keeping in mind that Pandas doesn't know everything, and sometimes columns containing values that are perfectly able to be converted to dates or numbers are still assigned that object data type. But fortunately, in those cases, it's usually pretty straightforward for us to override Pandas' choice and assign a more appropriate data type to the column. And we'll get lots of practice doing that in the next section. But back to the subject at hand, there's one more column of this output that I have conspicuously ignored up to this point, and that is the non-null count column. So before we can interpret what non-null means, it's probably a good idea to level set on what, null means. Well, in the world of data frames and databases for that matter, null typically means a missing or unknown value. So when our output here says there are 21,613 non-null values in the ID column, it's basically just saying there are 21,613 values in the ID column. Now, if you recall, our data frame has 21,613 total rows. So that means that the ID column has a value for every row of the data frame. And just scrolling down the output of our info method, it looks like that is also the case for all the other columns. But it is not always the case for every data frame you'll come across. Sometimes there are just flat out a lot of missing values in some of your data frame columns, which may be fine or may be a very big deal depending on which values are missing from which column. But in any case, the info method will help you zoom in on which columns are missing values and how many are missing. All right, so that's it for our little introductory level survey of inspecting data frames in Pandas. Up next, we'll transition to making changes to the structure of data frames, starting by renaming data frame columns. So one thing you'll find as you work with real-world datasets using Pandas or really any other data analysis tool is that sometimes the column names in those datasets aren't as clear, descriptive, or even as succinct as you might like. Now, other times, your organization might have specific naming conventions for those column names. Believe me, this is a thing. And the column names of the raw data you're working with may not follow those conventions. Now, in any of those cases, what we need to be able to do is rename columns in our data frames to names of our choosing. Now, we technically can do this at the same time as when we fetch the data into a data frame via read CSV, as we saw earlier. But that method is best used when the dataset doesn't have any column headers at all, not when we just need to rename a few hand-picked columns. That's because when you use that method, you have to supply a list containing all the column names of all the columns in the data frame, whether you intend to rename them all or not. So let's take a look at a more surgical approach which we can apply after we've already fetched our data into a data frame, which, as you can see, I've already done here to get us a head start on this video and get us right to the stuff we're actually trying to learn here. So as our example, let's say we want to rename the date and square foot above columns to make their purpose somewhat clearer. We can rename the date column to sale date so it's clear what that date pertains to, and we can rename square foot above to square foot above ground. I don't know about you, but when I first saw that column header square foot above, my first question was, above what? Now to do this, we'll be calling the rename method on our house sales data frame here. That method, shockingly enough, allows us to rename selected columns within a data frame. So let's go ahead and create a new code cell. And down here, I'll call that rename method on our house sales data frame. And this will be another case because since there are a number of optional arguments that can be supplied to this method, we'll need to supply the name of the parameter we're supplying our argument to. And that name is columns. And the value we need to pass to that columns parameter is a dictionary in which we will map the existing column names we want to rename to the new names we want to change those names to. And since we're only renaming 2 columns, the dictionary will be fairly simple, so I shouldn't even need to factor it out into its own variable. So the first key in my dictionary here will just be the name of the first column we're trying to rename, which is date. And then I'll just map that to the new name, which will be sale date. And then following that same pattern, my next key value pair will be square foot above. And then the value for that key will be square foot above ground. So now, just to confirm that this works, on the next line, I'm going to invoke the columns property on our house sales data frame to confirm that those column names were in fact changed. So I'll just say house sales dot columns and then run our cell. Now that's interesting. Our code didn't error out, but it looks like the column headers we meant to rename remain unrenamed. So what happened? Well, like many data frame methods, as we're going to see more and more of as we progress through the course, by default, the rename method does not modify the data frame we call it on in place. Instead, it returns a new modified version of that data frame. So one option we have is to simply assign the return value of the rename method to a new variable, and then just use that new data frame from now on. So what I could do here is say new df equals the return value of calling that rename method on the house sales data frame. And then down on the next line of code, I'll invoke that columns property on our new data frame. So now let's try running this cell again. And sure enough, we see that those column headers have now been renamed. We have sale date in place of just date, and we have square foot above ground in place of square foot above. Now another option we have that I generally prefer with these sorts of data frame methods, especially if we don't want to create a brand new data frame when we've already got a perfectly good one living in our Jupyter Notebook's memory, is to use the optional in-place parameter to specify that we want to make the change to the existing data frame in place. So let's create another code cell and paste in our code from the last cell in that one. And here, I'll dispense with all that business of assigning the return value of the rename method to a variable, and instead, I'll use that optional in-place parameter of the rename method, and the value I'll pass to that will simply be true. And now I can invoke that columns property on our house sales data frame and not the new DF data frame. And now running this, sure enough, our columns have once again been renamed, but without us having to go to the trouble of creating a brand new data frame to get it done. Okay, so now that we've taken our first stab at modifying the structure of an existing data frame, up next, we'll transition from renaming data frame columns to actually dropping columns out of a data frame entirely. So in the same way that the real-world datasets you'll find yourself working with on the job often feature column names that aren't ideal or usable for you or your end users, sometimes it's also the case that those data sets have a few extra columns that we just don't need as part of our analysis. And especially when it comes to larger data sets containing lots and lots of different columns, these additional unneeded columns just kind of get in the way. And of course, this means we need a way to remove those columns. And as is so often the case, Pandas gives us a built-in DataFrame method for doing just that, the drop method. So say, for example, in our house sales data set here, we don't feel like this ID column is providing much value. After all, the data set already has an index that was added automatically when we imported it with the readCSV method that uniquely identifies each row, so the ID column isn't really adding information or performing any function that isn't already covered elsewhere in the data set. So to get rid of that column, we can just call the drop method on the house sales dataset that I've already created in a notebook here, passing in the name of the column we want to drop, that of course being ID, as an argument. But it's not quite that simple. You see, the drop method allows us to drop both rows and columns from the data frame. So we actually have to tell the method which axis along which we want to do the dropping. That axis can either be 0, meaning rows, or 1, meaning columns. And you'll see this convention across quite a few different Pandas DataFrame methods. Now, a more user-friendly alternative to that 0-1 convention is to actually use the word columns if you're trying to drop a DataFrame column. And we'll actually go through examples that use both approaches. Now, to that, let's go ahead and get started by dropping that ID column. So in a new code cell, I'll call that drop method on our house sales data frame. And then because, again, like so many Pandas DataFrame methods, there are lots of optional arguments you can supply to the drop method, we'll need to specify the names of the particular arguments we're supplying. So first, to specify the column that we want to drop, we'll say labels equals ID, with labels, of course, being the name of the parameter that we're supplying that column name to. Then we'll say axis equals 1. And that, as I alluded to, tells this method that we want to drop a column and not a row. And then, because just like the rename method we covered in the last video, the drop method actually returns a brand new data frame as opposed to modifying the data frame it's called on by default, we'll assign the result of calling this method to a new variable. So I'll just call that new df. And then to prove to ourselves that that column has in fact been removed from the data frame, I'll just call the head method on our newly created data frame. So now let's run that cell. And then scrolling down, sure enough, the ID column is gone, and the date column is now the first column in our data frame. Okay, so that's what it looks like if you want to drop a single column from a data frame. But what if you want to drop more than one column at a time? Well, the only real difference is that instead of passing the name of a single column to that labels parameter as a string, you'll pass in a list containing, well, a list of the names of all the columns that you want to remove from your data frame. So let's say, for example, that we want to remove this square foot living 15 column from our data frame, as well as square foot lot 15. Now to do that in one fell swoop, I'll create another new code cell. And down here, I'll again call the drop method on our original house sales data frame. But this time, instead of supplying just a simple text string to our labels parameter here, we'll pass in a list containing the names of the two columns we're trying to remove. So that is square foot living 15 and then square foot lot 15. Now this time, instead of specifying that we want to delete columns versus rows by saying axis equals 1, I'll say axis equals columns, which is functionally equivalent, but for many people more user-friendly. Then finally, to circumvent the need to assign an entirely new data frame containing the modified version of our original data frame to a variable, we'll add the inPlace equals true argument, so this drop method just modifies our original data frame in place. So I'll say inPlace equals true. And then just to confirm this worked, I'll again invoke that columns property on the house sales data frame. And now running this cell and scrolling down, this time both columns we specified were removed from the original data frame that we called the drop method on. Nice. All right, so that's pretty much it for dropping columns from data frames. Pretty simple. So up next, we'll tackle the inverse of dropping columns from data frames, which is, of course, selecting columns from data frames. So while dropping columns from a data frame, like we did in the last video, makes sense if it's only a handful of columns you're trying to get rid of, if on the other hand, you want to exclude a majority of the columns in the data frame, it makes more sense to just select the specific columns that you want, instead of getting rid of the columns that you don't want. And we can do this by creating a new data frame, no in-place parameters this go round, containing just the columns we want. So let's say, for example, we want to select from our little data frame here the following columns: price, bedrooms, bathrooms, square foot living, square foot lot, and view. Well, it turns out that the syntax for doing this is ludicrously simple. So down in a new code cell, I'll declare a variable to hold the results of our selection operation, and I'll again call that new df. And then to extract those columns, I'll first reference the name of the data frame that we're extracting them from, in this case that being house sales, and then follow that with a pair of square brackets, and then inside that pair of square brackets, we'll actually need a second pair of square brackets. Now this second pair of square brackets is going to contain a list of the names of the columns that we want to select from that data frame. Now, since there's nothing especially advanced or exotic about typing out the names of columns, I'll go ahead and paste those in to this innermost pair of brackets to spare you from watching me type. And at this point, we've got everything we need in place to select just these columns from our original house sales data frame. So now let's run this cell. And nothing happens right away. But if we call our old friend the head method on this variable that we just created / declared, and then run this cell, we'll see a preview of what is in fact a brand new data frame that we created based on a subset of the columns of that original data frame. So again, this subset of our original data frame is absolutely a data frame in its own right, just one that only has the columns that we happen to care about. Now, one thing you might be wondering is why we need two pairs of brackets, what really looks like a list within a list, to specify the columns we want to select. Why can't we get away with just a single list? Well, there actually is a reason behind this, and you'll see what that is in the next section. My apologies for the suspense. But if you want to make this syntax a little more readable / user-friendly, you can always factor this inner list out into its own variable and then reference that variable inside the outer pair of brackets. So for example, I could just cut this entire inner list out and then assign that to its own variable, which I'll just call calls, and then reference that calls variable inside the pair of brackets after the name of our original data frame. So if I run that, and then run that head method on the resulting data frame one more time, everything still works just like before. All right, folks, that's a wrap for this video. I hope you enjoy your newfound powers of Pandas DataFrame wizardry, and that you use them responsibly, of course. And as always, I sincerely appreciate you tuning in. Keep your eyes open for more data-related content, and maybe even some AI stuff as well, very soon. I'll see you next time.